important research publications to his credit. He has been a research fellow and visiting faculty for many universities abroad. Sir has also supervised 20 plus PhD students, and he is also involved in the editorial activities of several journals. So we are blessed to have you with us today.
Thank you.
I request you to deliver your address. Over to you, sir.
Thank you. So you can hear me?
Yes, sir.
Yes, sir.
I'm going to share my screen now. So can you see the screen?
Not yet, sir.
You have not shared this.
Pratiksha, is he co-host? Sir, now try. I think so. Multiple participant sharing access is given.
Yes, sir, is a co-host.
Yeah.
Now can you see the screen?
No, sir, we can't see your screen. So you have to share the screen from.
Yeah, that's what I am doing.
Yes, sir, now the screen is visible.
Okay, thank you very much. And I wish all of you a very happy 15th National Statistics Day. So the title of my talk is on seasonal ARIMA processes. And then this is the outline. First, I will introduce the basics of seasonal process or seasonal variations of time series. Then just I will give you a brief introduction of ARIMA models. Then the concept and types of seasonality and SARIMA model. If I will get time, then I will also give you the details of ACF of SARIMA model and finally some concluding remarks. Now, at undergraduate level, many of you must have studied the traditional approach of time series analysis. And in traditional approach, what we do, we decompose the variations in time series into 4 different components according to the nature of the variation. The long-term movement of the time series, which is called secular trend. Then you have cyclical component. And as all of you know, the period of cycle is usually more than 1 year in cyclical components. You have seasonal components, which has a period of oxidation less, sorry, less than 1 year, and finally random or irregular components. Without random components, you cannot work in statistics. This is the component which makes your time series a random variable. And time series, you know that the current observation is affected by past observations or past shocks. In usual statistical inference, we assume that all the observations are identically and independently distributed. Ordering of the observations does not matter. It makes no difference in drawing inferences from the observations. But time series observations are not independently distributed. So the current observation may depend upon the past observations. Or you can say the past observations and past shocks also have some information about the current observation. Now, the Box-Jenkins approach is based on this logic. In Box-Jenkins approach, what we do, we try to model the current observation as a linear function of past observations and current and past shocks. So we assume that both past observations and past shocks are affecting your current observation. And that's why you write the current observation as a linear combination of these two things. In time series analysis, often you observe non-stationary behavior also. And this non-stationary behavior may be due to the presence of trend component. It may be due to the presence of unit roots and so on. One of the reasons may be the presence of seasonal behavior. This may also cause non-stationarity in the time series. Because if seasonality is present, then mean of the observations is not constant. Mean of the rainfall in July is obviously different from the mean of the rainfall in January or May. So it does not remain constant. It evolves according to a cyclical pattern. So you have some kind of periodicity. There are many examples of seasonal time series. You must have studied, say, monthly rainfall in Delhi. The rainfall is not constant and varies by months or quarters. For the same month in different years, we expect a constant expected value. You may expect the same expected value for rainfall in the month of June for 2019 or 2020 or 2021, provided it does not have any trend. Or even if it has any trend, the trend has been eliminated. Then there are many methods for obtaining seasonal indices, which all of you must have studied at undergraduate level. Simple averages method, ratio to trend method, method of linked relatives, etc. Now, the problem with all these methods is that these methods are unable to provide a link between current observation with the past observations due to seasonality. Means this is actually the basic difference between classical approach of time series analysis and Box-Jenkins approach also. In classical approach, we impose the 4 variations on your data. It has trend, it has seasonality, etc. In Box-Jenkins approach, the observations evolve, or the current observation has a link with the past observations. Now, just in brief, I will introduce the ARIMA models and then I will come to the main topic. So YT is a time series. Capital T is the set of all possible values of T. Then how we define the moving average process of order 1? MA, we also denote it by MA1 process. We write YT equal to mu plus UT minus theta 1 UT minus 1. So mu is the mean of the process. UT is always there, the present shock, the present error term, you can say. But apart from that, you also assume that YT depends upon just one period lagged shock, UT minus 1. So YT is generated by mu, the process mean. It has impact of UT, the current shock, as well as one period lagged shock, UT minus 1. Now, in terms of backward shift operator, you can write YT as mu plus 1 minus theta 1 B UT, where B is the backward shift operator. BUT is UT minus 1. B, if you replicate this backward shift operator J times, so B J UT is UT minus J. You can easily obtain the variance of the process, which is sigma square u 1 plus theta 1 square. Then you can also derive the autocovariance function. Actually, autocovariance function is obtained by the covariance between YT and YT minus K. You know, the time series, different time series observations are autocorrelated. They are correlated with each other. So their covariances may not be 0. For MA1 process, gamma 1 is equal to the first autocovariance coefficient is equal to minus theta 1 sigma square u. And apart from that, gamma k is 0 for all k greater than 1. So you can also write the autocorrelation function, which gives the correlation coefficient between YT and YT minus K. We denote it by rho K, which is equal to minus theta 1 upon 1 plus theta 1 square for K equal to 1. And for K greater than 1, it becomes 0. Now, similarly, you may define the moving average process of order Q, which is given here. So in moving average process of order Q, we assume that the current observation is generated by the current shock as well as by UT minus 1, UT minus 2, so on UT minus Q. So up to Q period lag shocks. Then and write YT as the MAQ process as YT equal to mu plus theta B UT. Theta B is taken as, this is also an operator, which is defined as 1 minus theta 1 B minus 1 minus theta Q B to the power Q. Now, this is the ACF of MA2 process. So for MA2 process, I have not given the expression, but the ACF vanishes after lag 2. In fact, for MAQ process, the ACF vanishes after lag 2. As I told you, for MA1 process, the ACF vanishes after lag 1. Right? So this is the beauty of moving average process. The autocorrelation function vanishes after a certain period. Now we define auto-regressive process of order 1, AR1 process as yt equal to say phi1 yt minus 1 plus delta plus ut. So here we assume that yt is affected by one period lagged values of y, means yt minus 1. This process is also called the Markov process because it satisfies the Markovian property. Given yt minus 1, it becomes independent of the past values, yt minus 2, yt minus 3, so on. Or you can write AR1 process as 1 minus phi1b yt equal to delta plus ut. And then you can easily derive the autocorrelation function of this process, which is equal to rho k equal to phi1 to the power k. Now here we assume that mod of phi1 is less than 1. So if mod of phi1 is less than 1, then how this rho k behaves? Rho k declines exponentially because mod phi1 is less than 1. So if you increase the value of k, rho k decreases, phi1 to the power k decreases. Now why you require this kind of condition, mod of phi1 less than 1? Suppose you take phi1 equal to 1, then see what happens. So I don't have time to go into the details, but I'm just giving you some idea. Say if you take phi1 equal to 1, then yt can be written as yt minus 1 plus delta ut, delta plus ut. Now you replace yt minus 1 by yt minus 2 plus delta plus ut minus 1. So you get yt minus 2 plus 2 delta plus ut plus ut minus 1, and so on. You keep on moving, then ultimately you get y naught, the initial observation, plus t times delta plus summation j equal to 0 to t ut minus j. Now if you look at this process, it has two important features, two important properties. First, it looks like that the process has a linear trend. T times delta. If you plot this process, it looks like that the process has a linear trend. In fact, the original process does not have a linear trend. So that's why this kind of trend is also called a stochastic trend. Many of you may know that this is a random walk model. So, and second thing, the error term is j equal to 0 to t ut minus j. So with lag, the impact of ut minus j on yt does not decrease. So it has a long-term effect. Any shock present in the time series has long-term impact. In fact, if you derive the values of this process, the variance becomes t times sigma square u. So as t increases, variance increases. So the process explodes. Explodes in the sense that its variance tends to infinity. Now, if you take the first difference, so although the process is non-stationary, but if you take the first difference, then it becomes yt minus 1 equal to delta plus ut. The process becomes stationary. So this is the graph of AR1 process with phi1 equal to 0.6. So you observe that the rho K, the ACF exponentially decreases to 0. In general, for the autodecreasing process of order P, ARP process can be defined as just for simplicity, we take delta equal to 0. So you can define the ARP process as 1 minus phi1b minus phi2b squares on minus phi p b to the power p yt equal to ut. Or you can write it as phi b yt equal to ut. So this is your ARP process. Again, I'm not going into the details, just I'm giving you a brief idea of all these processes. Then we may define the ALMA process also. The ALMA process has both autodegressive terms as well as moving average terms. So phi b indicates your autodegressive terms, phi b yt, theta b ut, this indicates your moving average terms. Order of autodegressive term is P, order of moving average term is Q. So that's why this process is called ALMA PQ process. P denotes the order of the autodegressive term and Q denotes the order of the moving average term. In general, as you have observed for the random walk model, if the process is non-stationary, you take the first difference, it becomes stationary. In general, suppose your original process is non-stationary. But if you take the d differences, then it becomes a stationary ALMA PQ process. Then we say that yt follows an autodegressive integrated moving average or ALMA PDQ process. So ALMA PDQ process means you take dth difference of yt, then the process becomes stationary. And this dth difference follows ALMA PQ process. And we write it as phi b delta d yt equal to theta b ut. Now we come to the seasonal processes. Again, yt is a time series and either trend is not present or we have already removed the trend component. And suppose yt has seasonal component and it has seasonality and period of seasonality is S. So whenever we say that the period of seasonality is S, it means if you take expectation of yt and expectation of yt plus S, then these two expectations are same. For example, for rainfall data, expected rainfall for July 2019 is same as the expected rainfall for July 2020 or expected rainfall for July 2021. Because the period of seasonality is 12 months. So expected value of yt is equal to expected value of yt plus S for all t. So this expected value of yt varies in its cyclical pattern, but it is a function of S. So it depends upon S. You can write it as a function of S. Say ST. For monthly seasonality, S is 12. For quarterly seasonality, S is equal to 4. You can have weekly seasonality also. On Sunday, you may find more people in the restaurants. So S is equal to 7 in that case. Now you observe this graph. This is the monthly data on ozone contents in the atmosphere. So the data has slightly decreasing trend as well as seasonality. To make the picture more clear, you may plot the graph for different months. So this is the graph for different months. So from this graph, you may observe that the ozone content in January is always less than that in May, or May is generally less than that in September. So this kind of conclusions you may draw from this graph. Or another option is to observe the seasonal behavior. Let us draw the time series for different months. So this is the time series for January. This is the time series for February, March, April, May, June, and so on. And then we have also plotted the mean, the average value. This average value may be the arithmetic mean or median. So it depends upon your choice, which measure of central tendency is more appropriate. You have to select. But if you look at these average values, then you observe some kind of seasonal behavior. It has decreasing trend as well as this seasonal behavior. Now, sometimes if you have very high frequency data, your time series is very long. Then instead of plotting this entire time series, you may use the box plot. Okay. So now we assume that except for its seasonal effect, the series is stationary and S is fixed. So you write YT equal to STS plus eta t. STS is the seasonal effect of period S at time t. And eta t is the stationary part after eliminating the seasonal effect. Expectation of eta t is equal to nil. So it has constant mean. It is a stationary process. Expectation of YT is then expectation of STS plus mu. Now, this expectation of STS is not constant for all S. So this series is non-stationary, right? Now we consider three different cases, three different types of seasonality. And then I will show that for all these three types of seasonalities, you can use the Sarima processes. The first case is when seasonality is a deterministic process. So STS is equal to STK plus S. So it's a constant function. So after period Ks, it is going to repeat itself. For example, if STS follows a sinusoidal function, like sine wave or cosine wave, which occurs in climate series due to Earth's rotation. But occasionally what happens, representing the seasonality component with sinusoidal functions is not very efficient. One can also use 11 dummy variables, one for each month of the year. Okay. Now the second case is seasonality evolves over time as a stationary process. So STS is a stationary process oscillating around a mean value mu s. So STS can be written as mu s plus mu t has mean 0. So basically this mu s is the deterministic effect of seasonal depending on S, and nu t is the stationary process and introduces variability in STS. Because remember, although we say that seasonality is periodic, it is oscillating, but those uh, periods have some variability also. Means rainfall of June of 2019 is not the same as the rainfall of June 2020. So there is some variability, and that variability is introduced by nu t. Third case is when seasonality changes over time with no fixed average value. So it's a non-stationary process. So suppose STS evolves according to a random walk. So it's a non-stationary process. STS is equal to ST minus S plus nu t. Nu t is a stationary process. Now you define the difference of operator of period S. Del S equal to 1 minus PS. Del S YT is equal to YT minus S. Then applying this operator del S to 1, you have del YT is equal to del S STS plus the first equation is YT equal to STS plus eta t. So del S YT is equal to del S STS plus del S eta t. Now remember the eta t, you have assumed that it is a stationary process, so it does not create any problem. The only problem is with the STS. We have considered 3 different cases, and for all the 3 different cases, we are going to show that this first part is also stationary. So suppose you take the first case when STS is deterministic, then if you take the difference, the seasonal difference, del S, then it becomes 0. So ultimately, del S YT is equal to del S eta t, which is also a stationary process. Eta t is a stationary process. So any difference of eta t is also a stationary process. The second case which we have considered is when STS is a stationary process. STS is equal to mu S plus mu t. Again, if you take the asset seasonal difference, then this part becomes 0. So you get del S mu t. So del S YT is equal to del S mu t plus del S eta t. Again, this is a stationary process, so it's asset seasonal difference is also a stationary process. This is also a stationary process. So this entire process is a stationary process. The third case is when STS is a non-stationary process. You assume that it is generated by a random walk. Again, if you take the asset seasonal difference, then the resulting process is a stationary process. Take the difference, then what you get here, del S STS is equal to nu t, because it does not depend upon S, so it becomes nu t. So it is a stationary process. So in all the 3 cases, we have shown that if you take this seasonal difference, then the ultimate process becomes stationary. Now, this result is actually the basis of Salimov model, of defining Salimov. So now you have the time series YT, Suppose your time series is non-stationary, then this non-stationarity may be of two types. First, it is non-stationary because it is a random walk. Or if you take the d differences of this series, then it becomes stationary. D regular differences, not the seasonal differences. So after taking d regular differences, this non-stationary part vanishes. Which non-stationary part? Which is caused by this random walk. And then to eliminate the non-stationarity due to the seasonality part, we take the seasonal differences. So to convert a non-stationary series with both seasonality as well as the second kind of, the first kind of non-stationarity, we use the transformation del S D del D Y T. Capital D is the number of seasonal differences. Usually we take 1 or 0, 0 when there is no seasonality, and 1 when there is seasonality. But sometimes you have more than one kind of seasonalities also. Means you have monthly seasonality as well as weekly seasonality. Although then the problem of estimation may be more complicated. And small d is the number of regular differences. Means like yt minus 1. And usually we don't go for small d beyond 3. Even 3 is a large number. Because each time you difference, you lose some information. So we model the regular and seasonal dependence separately, and then we construct the model incorporating both multiplicatively. So what we have done, this is your auto-regressive, regular auto-regressive operator of order P. Then you also have a seasonal auto-regressive operator of order capital P. This is your seasonal auto-regressive operator. This theta q is your regular moving average operator of order small q, and capital theta q ds is your seasonal moving average operator of order capital. Right? Now this is your SARIMA model. Seasonal auto-regressive moving average, so seasonal auto-regressive integrated moving average model. Right? Again, I repeat, this model has small d differences corresponding to your regular non-stationarity. It has capital D seasonal differences corresponding to your seasonal non-stationarity. It has these this auto-regressive operator corresponding to regular auto-regressive trend. This seasonal auto-regressive operator corresponding to seasonal auto-regressive trend. Similarly, this also has regular and seasonal moving average operators. Right? UT is your use of white noise process. And we write this model as, sorry, I should have written sorry, S also. S is missing here. So SARIMA P D Q cross capital P, capital D, capital Q, and this S denotes the period of seasonal process. So this model provides a good representation of many seasonal series. One can also derive the autocorrelation function for this process. So suppose now for deriving the autocorrelation function for this process, first I'm going to define the autocovariance generating function. So suppose gamma k is the autocovariance function. Then we define the autocovariance generating function as gamma b equal to summation k equal to minus infinity to plus infinity gamma k b to the power k. And then suppose you have this general linear process. Then for this general linear process, this is the autocovariance generating function. Now from this autocovariance generating function, how to get the different autocovariances? The procedure is very simple. Now this is a polynomial in B inverse. This is a polynomial in B. You multiply both the polynomials. Then first you collect the coefficients of say b to the power 0. That will give you gamma 0, means the variance of yt. You collect the coefficients of b, that will give you gamma 1. Collect the coefficients of b square, that will give you gamma 2, and so on. So finally, if you collect the coefficients of b to the power k, that will give you gamma k. Now for Saliman model, this is your stationary process. And you can break it into two parts. Or you can say two different processes. This is your regular ALMA process. ALMA PQ process. And this process has just seasonal parts, seasonal autodegressive and seasonal moving average operators on K. Now both these processes are stationary processes. And you know that if there is any stationary process, you can always write it as a general linear process. So you can write the first process as a general linear process. This. You write the second process as a general linear process, zt equal to this. Right? And then xt can be written as in this form. Psi b, capital Psi b as ut. So this is also a general linear process. So what we have done, first we have written the Saliman process. Is first we have removed the non-stationary part after taking the differences. Then we have written the process in two parts. First part, equation 7, as just ALMA part, the regular ALMA part, and the second part, equation 8, has just seasonal, autoregressive, and moving average parts. Then we have written both of these parts as general linear process, right? And then you can combine these two in this form, right? Now suppose Ci is the autocovariance, Ri is the autocorrelation of ALMA PQ process, 7 or 9. Then how can you get Ci? It is the coefficient of b to the power I in this. Psi b. Similarly, capital CSJ is the autocovariance of, and RSJ is the autocorrelation of seasonal ALMA PQ process 8 or 10. Then this is the coefficient of b to the power Sj in this. So ultimately, gamma k or rho k are the autocovariance and autocorrelation of the process 6 or 11 means the Sadima process, then you can easily obtain gamma k as the coefficient of b to the power k in this. Now, you know the coefficient of b to the power j in this part, you know the coefficient of b to the power sj in this part. So you can easily get the coefficient of b to the power k in this product. So ultimately you get this expression for gamma k, which you can easily find. For k equal to 0, you get the variance of the process, and then you can get the autocorrelation function, rho k. Okay. So for different values of S, small p, small q, capital P, capital Q, you can easily calculate rho k. Okay, let us see all these graphs. Then these graphs will make the picture more clear. Here you have MA112 process. So it does not have any regular ALMA component. It has just a moving average component, seasonal moving average component of order 1. The value of theta is 0.6. Now, it has non-zero autocorrelation at point k equal to 12. All other autocorrelations are equal to 0. Now, how the autocorrelation function for MA1 process behaves? Autocorrelation rho k for MA1 process is non-zero for k equal to 1. For all other values of k, it is 0. For MA112 process, for k equal to 10, it is non-zero. For all other values, it is 0. If you consider this process, AR112 process, then it is non-zero. It does not have any regular autoregressive or moving average term. It does not have moving average, seasonal moving average term. So this decreases exponentially with non-zero values at k equal to 12, k equal to 24, k equal to 36. Here actually S is equal to 12. We have monthly data. Now if you consider MA1, MA12 process. Now MA1 process has just one autocorrelation coefficient non-zero, which is at k equal to 1. Here also at k equal to 1, you get this non-zero value. Then this seasonal part you have, theta is minus 0.5. So you have negative value of rho 12. But not only these two values, two adjacent values are also non-zero. And these values are actually symmetric, means this value rho 11 is equal to rho 13. So the autocorrelation function of MA1 cross MA12 process behaves like this. If you consider MA112 process with theta equal to 0.5, then it behaves in a similar manner, except that these autocorrelation coefficients are non-zero. Now, if you consider AR1, MA112 process. Now, how the autocorrelation function of AR1 process behaves? The autocorrelation function decreases exponentially. But because of this MA112 term, it again starts increasing, goes up to this value for k equal to 12, then it starts decreasing, And since the order of this seasonal moving average term is 1, so after that you get no other such kind of increase in autocorrelation function. It just decreases exponentially, just like the autocorrelation function of AR1 process. The impact of this term vanishes after this here. Okay, so suppose you have this process AR1, AR112. So you have usual AR1 term and then seasonal AR112 term. So the autocorrelation function behaves like this. It decreases exponentially, again it starts increasing, decreases exponentially, then goes up to this point, it starts, sorry, it increases, then decreases, it again starts increasing, goes up to this point, decreases, and so on. And if you look at these points, these maximums are also decreasing exponentially. So this is how the autocorrelation function of all these processes behave. We have considered an example also. We have taken ZT equal to del 7 YT, and then we have calculated the autocorrelation functions for all these processes also. Well, I am not going to much details, but we have plotted the autocorrelation functions for real data also. So here are some concluding remarks. So seasonal autoretracing integrated, sorry, this should be M, moving average model accommodates both non-seasonal and seasonal factors in a multiplicative way. And this multiplicative model can be generalized for more than one type of seasonality also. Here we have considered just one type of seasonality, a seasonality with period S. But sometimes in applications, you may have more than one type of seasonality. Although in those cases, estimating the coefficients becomes more tedious, more difficult. So here are some differences. You may go through all these books. That's it. Thank you. Any question?
Yes, thank you so much, sir. Are there any questions, dear participants? If you have any questions, please put them in chat box, or you can unmute yourself and speak. If there are any questions, please put them in chat box, or you can unmute yourself and speak. So I think sir has very nicely explained the SARIMA modeling, and his students, participants don't have any questions right now. So we'll go ahead with our program. Thank you so much, sir, for your very enlightening and motivating and very informative address. You have explained it, the time series SARIMA modeling very nicely and very systematically. We are happy to have you with us today, and thanks once again on the behalf of Department of Statistics. So,
well, actually, sorry to interrupt.
Yes, sir. Yes, sir.
If there is
There is one question, sir. Yes, there is one question right now. So Adil Kamal is asking how heteroscedasticity effect affect time series.
Heteroscedasticity in what? In random component or in UT, or I think in UT.
Yes, Adil, you can unmute yourself and speak also. In what? Yes, UT is saying.
UT, okay. yeah, then the problem will be more complicated. Then you have to go for some um, processes like R or GARC processes. And those models, your variability also is the variance of ut, you assume that sigma squared t, and sigma squared t is also generated by some process. So problem will be more complicated, but you can find work on arc and GARC models also. So
Yes.
one thing I want to mention that in SADIMA models, we take the seasonal part of the operator and the usual part of the operator in a multiplicative way. Now, if you don't consider this kind of uh, multiplicative way of constructing the model, then imagine what will happen if, without taking into consideration the seasonality, you plot the ACF, then you will get this kind of ACF which I have shown you. Okay, and then what you will do? You will fit an a moving average model of order 12 or 13 or 14, or an autoregressive model of order 36 or 24. So then that will be very tedious. Is in between the auto correlations are almost zero. And suddenly you have a significant autocorrelation coefficient at s equal to 12, or s equal to 24, or s equal to 36. Sorry, k equal to 12, k equal to 24, k equal to 36. So if you are not going to consider the SARIMA processes, then you will get confused whether you should fit AR1 model or AR12 model or AR24 model. So in those cases, if you have significant autocorrelations at some periodicity, then it gives you indication that your time series has some kind of seasonal. Okay, thank you.
Thank you so much, sir. I think almost everybody has liked the session, and they have written good comments in the chat box. So I think, Asha ma'am, shall we proceed further? Asha ma'am?
Yes, Pratiksha, I'm here. Sir. Thank you very much, sir. Thanks a lot, Million, for such a short notice. You have accepted our invitation and brighten our day with your knowledge and with your expertise comments.
Friends, now we are reaching towards the end of this inaugural session. Post lunch, we have competitions for students. So, before we end our session, I would like to invite my fellow colleague, Ms. Shailaja Rani ma'am, to deliver the formal vote of thanks. Over to you, ma'am. Shailaja ma'am, you are not audible. So, dear participants, the feedback form for third session is also floated in the chat box. I request you all to fill up the feedback form for all the three sessions. If you have not filled up earlier two sessions, please fill up those feedback forms as well. The same will be considered for the attendance purpose as well. So it's a request to fill up the feedback form to everyone. I think Shailaja ma'am is facing some connectivity issues. We will wait for 2 minutes. Otherwise, I will continue with the. Yes, I think Shailaja ma'am is joined back. Ma'am, are you able to? Yes, please make her a co-host. I think she is not able to unmute herself.
Yeah, hi, I'm very, very sorry. Can you hear me? Can you hear me, Pratima, now?
Yes, yes.
Yes,
Yes.
yes, yes. Thanks a lot. Thanks a lot. Okay. A very, very happy National Statistics Day to one and all. Okay. Good afternoon to all the dignitaries present today, and a very good afternoon to my dear colleagues and participants of the first day of our 4-day national conclave. I, Mrs. Shailaja Jirane, would like to propose the vote of thanks to all those people who are instrumental in making today's program a grand success. First and foremost, let me thank Government of India for deciding to celebrate Professor Prasanta Chaudhary Mahalanobis' birthday as National Statistics Day. We are blessed. Also, I would like to thank Dr. Mahalanobis himself in his absence for his contributions in the field of economic planning and statistical development. I would like to thank our chief guest for today, our dear Dr. Niranjan Hiranandani sir, Provost of HSNC University, Mumbai, for his valuable inputs and making his speech so witty that with all the applications of statistics in his field, that is real estate, okay, and making the program lively. Thank you, sir. Our dear principal ma'am, Dr. Hemlata Bagla, always believes in updating ourselves. She believes in the coexistence and partnerships of academics with industry. She motivates us to search for avenues to make the learning process interactive, and she always tells us to make the students industry ready. Thank you, ma'am, for your guidance and motivating us to think big and better. In the early 1900s, statistics and statisticians were not given importance. But over the years, due to the advancement of technology, scope of statistics widened. Also, due to the interdisciplinary approach, the importance of statistics has grown exponentially. We at KC College always believes in bringing the best to address our audience. So our eminent speakers, Mr. Mukesh Jain, sir, who couldn't come today because of his other things. I think he is present somewhere else. Mr. Prashant Nair, sir, Director Nielsen, Dr. Rajesh Singh, sir, Professor, Department of Statistics, Amravati University, and last but not the least, Dr. Anup Singh, sir. Now, these people had made our statistics the best. They had explained us, they had enlightened us about the role of statistics in artificial intelligence, okay, which we missed actually today, the country's development, and also how data can be used or how the bad decisions will affect us, was very well explained by Prashant Nair, sir. Majority of the events nowadays are time dependent. Dr. Anup Chaturvedi sir's Sarima models for predictions was very, very informative. Thank you all for making us understand the importance of our subject. I would fail in my duties if I don't acknowledge the contributions of our vice principals of KC College, the 4 strong pillars of KC College, Professor Padi sir, Dr. Shalini Sinha madam, Professor Justin sir, and Dr. Tejashri Shanbag ma'am. Thank you all for helping us in conducting this program smoothly. 4 years ago, Dr. Asha Jindal had become the HOD of our department. She had thought of introducing new concepts and events which benefit students and also faculty. One such event was National Statistics Day, which she started. Initially, we started by celebrating this day on only one day, that is on 29th June. But now she had converted it to a 4-day national conclave with lots of qualitative interactions, fun-filled and knowledge-imparting games, competitions, and presentations. From the bottom of my heart, I appreciate her for bringing in new ideas. Thank you, Dr. Asha Jindal. During this pandemic period, we really understood the importance of our technical team for smooth running of our programs. Thank you, Roshan and his team for his technical support. Nothing would be possible if we don't have our office staff's support. Thank you all. The grand success of any program is mainly due to the participants who attended. Thank you all for sparing your valuable time and boosting our energies with your interactive participation. How can I not thank my team statistics? Ms. Pratiksha for her flyers, brochures, speeches, and whatnot. Dr. Mulesh sir for his meticulous organization. Our young team, Ms. Anjali, Mr. Suraj, Dr. Aradhna, Ms. Aisha, and Ms. Kismat for bringing freshness into our ideas. Of course, our backbone, Santosh Sarvankar, for helping us behind the scenes. This program, of course, is a team effort and a team success. Thank you all. Over to you, Pratiksha.
Thank you so much, Shailaja ma'am. Now we will have a break for lunch, and post lunch we are going to have competitions for students. So I would request students to join back around 1:30 for the competitions. Is that fine, ma'am?
Yes, Pratiksha, it's all right.
Students,
So
and-
I think so in half an hour, they can remain on this platform and take a break. Choice is there. And then they can, because later on they should not say that there was a problem, glitches.
you can either stay back or you can join back.
Choice is yours. You can be here. We are also here only, maybe around these.
Other participants, faculty members, and other participants, please fill up the feedback form, and see you all tomorrow.
Not tomorrow, today itself, after the lunch break. After the lunch break, yeah, faculty
Participants,
members.
I'm saying.
Participants. Yeah, faculty members, yes, please. Tomorrow join us at the 10:15 sharp. 10:15 sharp. Because tomorrow's session will start at 10:30 sharp. So please join us at 10:15. And all the student participants, either be here or please join back, because there are many more things for you.
So thank you so much, all the faculty members who have joined from the various parts of India. Hope to see you tomorrow again at 10:15 a.m. Thank you so much. And dear students who are going to participate, please join at 1:30. You can take a short break of 20 to 25 minutes. Thank you so much. Thank you so much, Monish, for handling it so well, handling the technical part so